Hello and welcome to the Uthermal channel. As a system approaches a state of thermodynamic equilibrium, does the diffusional mass transfer of a substance occur from a region where its concentration is high to a region where it's low? As a general statement, is this true or is this false? The goal of this video is to answer this question. It is possible to answer it in several ways. Here, we'll use a system with two chambers, separated by a membrane. On the right-hand side, we have chamber 1 that contains pure solvent. On the left-hand side, we have chamber 2 that contains a solution of a solvent and a solute. Between them, there is a membrane that's rigid, permeable to the solvent, and impermeable to the solute. We will assume that this system is kept at constant temperature. Let us find the condition of thermodynamic equilibrium, in which the fugacity of the solvent in chambers 1 and 2 will be equal. I emphasize the fugacities will be equal, not the concentrations. Equation 1 gives the fugacity of the solvent in the liquid solution, that is, in chamber 2. It is given by the product of the mole fraction, by the activity coefficient, by the vapor pressure, by the fugacity coefficient at saturation, and the exponential of this integral that appears in equation 1, which is called the Poynting correction. The Poynting correction depends on the molar volume of the solvent in the liquid phase. If we assume that the solvent in the liquid phase is incompressible, this molar volume is constant, and we can simplify equation 1, obtaining equation 2. We will now assume that the liquid solution in chamber 2 is ideal, and we will apply logarithm to both sides of equation 2. This gives equation 3. We can apply a similar set of assumptions to find the fugacity of the pure solvent in chamber 1, and we obtain equation 4. Imposing the isofugacity condition to find the state of thermodynamic equilibrium, we obtain equation 5. In it, if we cancel out the common terms, which are the vapor pressure and the fugacity coefficient at saturation, we obtain equation 6. Equation 6, after some manipulation, leads to equation 7. The pressure difference between chambers 2 and 1 appears on the left-hand side of equation 7. This is the pressure difference that exists between the two chambers at equilibrium. This pressure difference is called osmotic pressure, and we normally use the Greek letter pi to represent it. Equation 9 shows that the osmotic pressure depends on the temperature, on the molar volume of the pure solvent, and on the solvent's mole fraction in solution. Therefore, at thermodynamic equilibrium, the pressure in chamber 2 is equal to the pressure in chamber 1 plus the value of the osmotic pressure. An interesting question is what happens if we displace the system from the condition of thermodynamic equilibrium by applying a pressure P2 larger than P1 plus pi. If we do that, there will be a net solvent flow from chamber 2 to chamber 1. But observe the following. In chamber 2, we have a solution, and the mole fraction of the solvent is less than 1. In chamber 1, we have a pure solvent, and of course its mole fraction is equal to 1. Therefore, when the solvent moves from chamber 2 to chamber 1, it moves from a region of low concentration to a region of high concentration. In many cases, the diffusional flow is from the region of high concentration to the region of low concentration. But the situation used in this video illustrates the opposite case, in which the flow is from the region of low concentration to the region of high concentration. In summary, it's not the concentration difference that dictates the direction of the diffusional flow. Then, if it's not, what property difference will have a clear connection to the flow direction? To answer this, let's again assume that the pressure applied to chamber 2 is larger than P1 plus pi. By examining the expression for the fugacity, which appeared before, we see that increasing P2 will increase the fugacity of the solvent in chamber 2. So while still away from the new equilibrium condition, the fugacity of the solvent in chamber 2 will be larger than in chamber 1. But remember that we identified a net flow of solvent from chamber 2 to chamber 1 under these conditions. Putting these two observations together, what we find is that the direction of the diffusional flow is dictated by fugacity differences and not by concentration differences. The overall conclusion is that the fugacity difference drives the diffusional flow. Instead of fugacities, we could have used chemical potentials for this analysis. Had we done that, our conclusion would have been that the diffusional flow occurs from a region of high chemical potential to a region of low chemical potential of a given substance. We hope that this video has contributed to clarifying the relationship between concentration differences, fugacity differences, and the direction of diffusional flows. Thank you very much for watching this presentation. My name is Marcelo Castier. Goodbye.